Do you want to record on my side or are you good?
Uh, I think I'm good. Yes, I'm good. Yeah,
Okay, cool.
nice.
Oh, my computer's slow.
I'm
So
preparing
wait, how's it
my,
going? What?
yeah, I'm preparing my you remember the last time I tell you my neural network from scratch?
Yeah, I remember.
Yeah, I can admit it for you, like my project was going on.
Do you want to go first? Because
You can go
mine's
first. Yeah, you can go first. Yeah. Yeah. Did you get the email from them yet for the employment thing?
what email?
Like they sent me an email saying like
To
I
clear it?
can, yeah, activate my UCI net something and then like try to set up my payment and everything else.
I didn't get that.
You get, yeah. Okay.
I'll check after this.
Okay. It will come in
Hey,
soon, I guess. Yeah.
Triet, my thing's really slow. Do you want to go first?
Yeah, sure, yeah. But you have to enable me to that screen too. Here you go. What about last time? Mm, okay, last time it was softmax activation. And simply you want to check into the last time before softmax is linear rectify unit, which if the value is negative, you flat out to zero. And if the value is greater than zero, it stay the same. And then from that, you involve the softmax, which take into account the negative number. You want to take the meaning of negative number. And then as a softmax, I learned about loss function, which is simply a neural network. It's just you're interested in the loss function because as long as you have the loss value, you can adjust the weight and the biases in a way that you want to minimize the loss function. In that way, you got, because here, when the loss like reduce, you kind of fit the curve you created, fit with the data.
Wait, I have a
Mhm.
question before I go on, if you don't
Yes.
mind. So I've always wondered like why ReLU is considered a nonlinear function. It always struck me as kind of odd, but now I can kind of understand because this curve, it's linear, but then it has these angles, where
Hmm.
because part of it would go to zero. And so
Hmm.
it's technically nonlinear, even though it basically is just a connection of linear functions, but they change, right?
I mean, it's not linear. It's just straight, right?
Yeah, but it's composed of a bunch of straight functions if you look closely.
Yeah, but it's not linear because I mean, when you take linear algebra,
Yeah.
the order has to be one. It can't go like this and then this, right? You can have two roots at the
No,
same time.
I agree. I agree it's nonlinear, but it's just odd.
I see. Yeah.
It's like it's nonlinear, but it's composed of a bunch of linear ones.
Yeah. But it makes things nonlinear that way. Yeah.
Yeah.
And then it
Yeah.
combines together. That's pretty good. Yeah. And then
Yeah, because
okay.
I was looking
Yeah.
because last week I was looking at activation functions and I thought Rarely was in a weird one, and it works. It apparently works really well. But
Hmm.
yeah,
Yeah.
you can
And
continue.
yeah, it's very computational like too. So like because the function is so simple, you can compute very quick. But anyways, yeah, with the last function. The last time I tried to explain this, but I wasn't very sure. This time I'm a lot more confident. So this is the class which is specify the length of the one hot vector. And the label is the index where in the one hot vector is going to be one. So in this case, class is three. So that's the length of the one hot vector is three. And the label is zero, which is the index zero. The value is going to be one, and the rest is going to be zero. And so this is the prediction that we got from the neural networks. And this one hot vector is the data, the real data that we're going to use to train the model. So for example, this is a categorical cross entropy. So technically you have a neural networks. For example, you input an image of either a dog, a cat, or a fish, and then three categorical, right? And then, for example, the first one is cat, for example, then you're gonna hard encode it. So the first one is gonna use 1, 0, 0 for a cat image. But for the a neural network, when it outputs, it's only output a probability that it guessed. So 0.7%, so 70% that is, it guessed that it's a cat, and like 10% it guessed it's a dog, or, and then 20% it guessed it's a fish. And for that, we want to see how right or how wrong it predict. And from that, how right or wrong, we can back propagation and adjust the weight and biases. Because the loss function, for this kind of loss, is simply you take the log of the natural log of the predicted, so log of 0.7, then you time the one hot vectors. Then you take log of 0.1 and you time 0. You take log of 0.2 and you time 0. And you add all them up, and then you put a negative sign in the front. That is the mathematical operation. Okay, and then this is exactly the same what I just say. You have a output. This is output from the neural networks. You have a target class, which is 0. So, for example, this one is a cat, for example. The so for the real data, the image is a cat. So you can have a one hot vector with 1, 0, 0, because the index is 0 here. Then for the loss, you technically take this mathematical operation, you put it in, just log of the predicted value of the neural networks, and you time the value of the one hot vector. So if you notice, this is 0, 0, so the other two value cancel out, and only this 0 log of 0.7 matter. And then I did check a few times over here to make sure I got the correct value. But this one is just with one input value. When you do when you run a normal neural networks, you don't run one input at a time. You run like a batch of them, so like multiple input at a time. And when you end up having a matrix instead of a single vector, and this one is my attempt to deal with matrix instead. And it's pretty much the same because if you have NumPy, you can use array with NumPy, and array is very convenient, and it's pretty much the same thing because of the NumPy thing.
I have a question because
Yes.
I'm working with looking at the code from the paper to understand how they work.
Mhm.
What exactly does NumPy mean?
Oh, NumPy is a library. It's contain a lot of things in Python. It's a
Okay,
very popular library. Yeah.
so PyTorch would be a more advanced library
Yes,
that
it is.
has a lot of
Yeah.
the functions that you are describing yourself from scratch, but they come prepackaged in PyTorch, right?
Yes, PyTorch is a lot more advanced, I believe. It's very close to like current machine learning.
So why aren't you using this for your neural network? Do you just want to understand it better if you build everything up with
Yeah,
all
like
the math?
yeah. I actually want to understand like what's inside the PyTorch, like what's going on behind the scenes, right?
Hmm,
And this is why I actually build them without using the existing library. So I'm literally building their library right now.
I
Yeah,
see.
just to know what's going on behind them. Yeah, and it's very good to like understand some of them too, because I never think about them when I do a broad picture, but now when I go deep into them, there's a lot of like little things that I didn't notice before. Yeah.
Yeah. Like with the loss function, there's one I'm looking at is cross entropy, and what it does is it would actually take the ones that are zero into account, where it adds like the complement of that loss function.
Compliment.
So
Mm.
it's hard
Oh,
to explain, but it would like
yeah.
from this from the function you're showing me, it would subtract um the complement of the one hot vector and the complement of the prediction.
What do you mean by compliment? Uh, Like
Well,
example
one minus them.
example. Oh,
One
one
minus
minus.
them. So you would have the loss function, and then you would subtract from that 0, 1, 1, 1 is one hot, and the prediction would be zero point 0.3, zero point 0.9, and zero point 0.8. It's interesting.
Oh,
But yeah,
okay.
that's also it's a
I
loss
see.
function that takes into account the stuff that is false so that
I
you wouldn't
see.
be taking account for this one.
I
Yeah,
see.
it's interesting.
Yeah. So do you know why, or like is there any reason for that?
Well, it's the loss function that was used in the paper.
Oh,
Um,
okay.
and it was weird because it was this compositions, so it was treating compositions as though they were probabilities.
Mhm.
It's a bit strange, but you'd use that function. That's why I'm aware of it.
Okay, let's see. Now, normally
I don't know if
there's
it's
a good reason behind it. We just don't know what it is.
yeah.
Yeah, it's good to know. Yeah, but yeah. Anyway, yeah. So this is a okay. Back to this loss with multiple output. So instead of one output, it's going to be a matrix instead of single vector. And there's three rows, so three iteration of three times the input is put into the neural networks. So this is the first time the input. This is the second input. This is the third input. Each input had three values. So this the column, the number of column is the number of values in each input, or the number of initial neural, if you think about it that way. For the target for the one hot vector, instead of bringing the whole one hot vector in, we're just going to be interested in the index of the number one value in the one hot vector. So instead of put like the whole thing in, I'm just input in the index I want. So like for example, 0 is 0.7 I'm interested in, and 1 is 0.5. The last one is this 0.9 is the index. So um, next is I want to extract the values that I'm interested in from this softmax output. So the way I do this is I take the softmax output, and this is simply a index thing, because softmax output is a matrix, and you can index a matrix with x and y value. So it is row and then column. The first one is row, and for row it looks complicated, but it's simply 0, 1, 2. That's it.
Wait, I'm sorry for interrupting, but I'm a bit confused. Is the class targets, is that a mask?
Class target.
Or is
Oh
something
no,
different?
it's you know the one hot vector I put in front here, right?
Yeah.
So I like it's included one, only one value is one and the rest is zero, right?
Hmm.
And so like instead of doing, so this is one input only. So if you do three input, then you're gonna need three times this, right? Three times of this.
Hmm.
So it's the whole matrix. But then like only one of them is one and the rest is zero anyway. So you only care about like the index that is one. And with that value, you can extract the value from this easily.
So this is like when you train it with batches, right? And so the batch would have
Yeah.
multiple inputs,
Yeah, multiple
right?
input. Yeah.
Okay.
Yeah. So instead of the whole matrix of a one hot vector, I'm just gonna do the like the index of the value one in the one hot vector instead.
But wouldn't you need, and for the class targets, wouldn't you need a full array instead of just one vector?
I mean, it doesn't really matter as long as you have enough information to like take out the number
Okay,
you
so
want. Yeah.
would each of those inputs, they would all give you the same output, so you don't need a full matrix?
Yeah, you don't need the full matrix, right? Yeah. Like
Okay.
because the matrix is just including one and zero, right? And like each row has only one number one. So as long as you know the index of number one in each row of the matrix, you don't need the whole matrix. You just need one vector to tell you index of the number one in each row of that matrix.
Okay, so the first row, is there no one? Or is the one I'm confused.
Yeah, so
Okay.
okay. I can show you. Let me see if there's anything I can show you. I think this is gonna be uh, oh yeah, here you go. Yeah. So for example, this white truth, this is the real data, right? And this is three one hot vector. So the first one hot vector have a number one at index zero. The second one hot vector have the one at index one, and the third one hot vector have number one index at one. Yes, right. And so instead of the whole matrix, you know that each row in this matrix have one number one. So the only thing you need to know about this matrix is the index of the number one of each row. So this matrix is, you can reconstruct this matrix with this one vector right here. So number 0 is the
Oh,
0
oh,
index.
I get it now.
Yeah.
Okay,
And
I'm
then,
sorry if it took a while to understand, but yeah, I understand now.
yeah, again, that's nice. Yeah. And then, okay, here you go. Here it is. Yeah. So instead of the whole matrix, I had just one vector instead of the whole matrix. And then from this, I want to extract the necessary number from the softmax matrix. And the thing is, if you look at the lot function, right? A lot of them is 0, 0, they cancel out anyways. So the only value that you're interested in is the value that match with the number 1 in the one hot vector. And that's why we have this. We only extract out the necessary number, the number that we're interested in. So for example, we have the first row, the index we're interested in is 0, right? So this number is the only number that we're interested in. The second one is 1. So for this one, the only number that we're interested in has index of 1. So the next one is 0.5. And by the way, I'm not sure if you know this, but for Python, index start at 0. So the first is 0, and the index
Yeah, I
is
noticed
1.
that
Yeah, okay. Okay,
when I
yeah.
was working with trying to understand the code for the paper.
Mhm.
I noticed, yeah, the sort of zero.
Yeah, right.
It was confusing at first, yeah.
Yeah, yeah. And then this is 1. So we're interested in this value, right? Um, and then yeah, we simply extract it right here. Just this is the matrix of the softmax matrix. And then this a bit complicated, but it's simply say 0, 1, 2. So it's index in the row, and it's just top to bottom, 0, 1, 2. And this one is just generalized when you have like bigger matrix. You have 4 rows, it's gonna go from 0 to 4, 0 to 3. And you have like more rows, it's gonna just continue doing that instead of you like hard code the number in. For the class target is simply this the index we're interested in, because the index is also matched with the number of columns in the matrix. So for example, um, the first one is in this one is going to be 0. So the 0 row, and then the first one in the class target is going to be 0. So it's going to be the first column, first row, first column, going to be 0.7, which is what we're interested in. Then we continue doing that. Second row, right? It's going to go to number 1, the second row. This one's going to go to number 1. So also second column, you're going to get this number. And last one, this one's going to go to the third row, which is this one. And for class target, it's going to go to number 1. So it's going to be 0.9, which is what we want. Then after that, I print out a few stuff. And then you can take the log of all these values. So far, if you look at the loss function, I extract out, so for example, for this, I extract out 0.7 already. So I take the log of 0.7, and then 1 is doesn't really matter. And then you take a negative and you're done with this. So over here, I simply take the log of that number, but not just one input, but it's like 3 input at the same time. Then I print out the loss. And then this is the average loss. So for a batch, you don't just calculate one loss. We have like 3 loss for 3 times the input, right? So just for convenience, you just take the average of them. And that's how they do it in the normal neural networks too. And then the some value I printed out, the values before the log function. And then, so this is all the value that we are interested in too. And then you take the log, and then you do the average, negative log average, yeah, that's it. And this is where I apply the loss into the whole code. So the whole code is kind of complicated. Did I explain the whole code for you before? Or
I think so.
yeah, I can
Wait,
go
I'm not
over
entirely sure
again.
what exactly you're trying to find.
Yeah,
I don't understand the math the math behind what you're saying.
yeah. I can explain again if you want.
What are you trying to measure or predict with this?
This is just a random um, data, frankly. There's nothing special about the data. I just want to apply this into the data and just random stuff. But yeah, but yeah, like this is pretty similar to what's inside PyTorch, I would say. Because when you use PyTorch and you call out like layer names, it's exactly what I'm coding right now.
Yeah.
Yeah. I
What are your
mean,
goals for this? Like after you get it all made?
uh, what do you mean like I go for the data?
Well, like are you just trying to like create a neural network from scratch and understand how it works?
Yeah,
Or are
I'm
you gonna
doing.
like try to build something with it? Like
No, I'm just creating from scratch to understand how it works. It's just for
I see.
understanding
Okay.
purposes. Yeah, yeah. It doesn't have any important meaning or anything. Yeah.
I'm
Just
are
yeah.
are you done by the way? Or
Oh yeah. Totally. Yeah, yeah. Done with this.
I'm
Yeah,
trying to
and
think if
then
there's any questions I have.
yeah, and
No,
then
I'll
yeah,
just say this and then you could explain more.
yeah.
My approach is kind of the opposite. I'm kind of rushing through it a little bit using PyTorch to do most of the work. Um,
Oh, I see.
and I'm
Yeah,
just
yeah.
trying to create a neural network that will just kind of
Mm,
generate material compositions with better properties than average.
I see.
We'll
I
see if it
see.
works. We'll see if I finish it by the end of the summer.
Yeah, yeah.
But I've just been like the math with Wasserstein distance. I
Hmm.
guess that's kind of the most in-depth stuff I've been doing recently.
I see. What's this again? This. Yeah.
Yeah, pretty
Okay.
involved.
I see. Yeah. I mean, we have different approach, but I think that's pretty good because like the
We're
things that
not
I
doing the
don't
same.
know. Yeah, yeah. And then we can like
We're doing
supplement
different
each
things.
other.
Yeah.
Yeah. I can learn more from you and you can learn from my project too.
Yeah.
That's good. Yeah. Nice. Your presentation's ready?
Well, I don't ask you some stuff first. So this has to do with like batches, right? Where you
Yes.
train it with batches.
Yes. Hmm.
I was gonna look into more stuff like this tomorrow. So like what's the difference between stochastic gradient descent and batch gradient descent and semi-batch gradient descent?
Oh, okay. I haven't get that yet, but
Okay.
yeah. Yeah. We'll see. Yeah.
Because it's like different ways of because you wouldn't train it on the whole data set at once. You train on like random snippets one at a time. So
Hmm.
just some there's different ways of doing it.
Yeah. I mean, for now the weight is like random. I don't I don't know. There may be a specific set way that can help you get the correct number faster, maybe something like that.
Oh, is this for initialization?
Yeah, initialization, the way is random. But I don't
Yeah,
know.
I could probably find this. There's some resources on how to initialize it.
Hmm.
There's like certain techniques that people have found that are like the best places to start that
Oh,
helps it find the local minimum quickest.
oh,
Um,
okay. I
it's
see.
been a while since I looked at it, but yeah,
Okay.
I don't know if there's exactly one way of doing it though, because eventually you'll get to the right answer. It just may take longer.
Hmm. Yeah. Oh, okay. I mean, I will worry about it later.
Yeah.
Yeah. Okay. Yeah.
All right, cool. Do you want me to share my screen?
Yep. Yeah.
Wait, hold on. I'm actually not ready. Discord hasn't loaded. Oh no, it has. Okay. So I've essentially repurposed my original presentation.
Hmm.
I took some stuff out and then
Hmm.
added some more things
Hmm.
because that was about variational autoencoders.
Hmm.
So when I first started this, I didn't know what the Wasserstein distance was, and now that I know a bit more, let me just wait till I get there. So I'm not going to be comprehensive with this. I'm going to kind of wait. Am I breaking up?
Yeah, I haven't seen a screen yet, but yeah.
Okay, can you hear me fine?
I can hear you fine. Yeah.
Okay, cool. Okay, so when Cal says that there's going to be the group meeting soon for everyone, undergraduates and graduates,
Yeah,
I'm
for
going to go into more
August.
depth. But
Yeah.
yeah, I'm. Wait, do you know what date it will be at?
No, I don't, but it's gonna be August meeting, so well, it's right now it's just the beginning of August, probably like mid-August or something.
Okay, so I'll probably be quite a ways through then by the
Hmm.
time that comes. I'll probably add to this more. This will just be a preliminary discussion about what I'm planning.
Mhm.
Okay, let me. This thing's still loading.
You should upgrade your internet plan.
I'm thinking about getting a new computer. This is like an old PC.
Oh, okay. It's about computer and not the internet.
No, it's slow on a lot of things. It kicked me out of Python today because it didn't have enough space.
Hmm. Hmm. My computer, I think I remember it was like 800 when I bought it on Black Friday. That's pretty good.
I probably should turn my video off. I probably don't even need it anyways.
Oh yeah, yeah.
This should help.
There you go. Still loading.
And it's still loading.
Oh.
Am I still showing my screen?
No, you're not.
Finally, okay.
Mhm.
Okay, so this is pretty basic. Me, and
Oh,
probably people watching this are going to know what this is. So autoencoders are pretty much they're just neural networks that take in inputs, compress the data, and then try to extrapolate from the data they compressed back into something very similar to the inputs that was given. There's a lot of different forms. The thing is, so neural networks, they're pretty much just a network of nodes where you have certain inputs and then those connections between them that will add a bias and then will weight each previous input to the next input. And then these can go on for several layers until you have the output. I'm gonna rush through this. Okay, so with autoencoders, I think I skipped a slide. Okay, a variational autoencoder. So instead of just compressing the data, it will make the data a smooth distribution. And this is so that we can interpolate between data points. Instead of because a lot of times autoencoders, if you try to get it to predict a data point that it wasn't trained on, it will just give you nonsense. But this will help that. It's also a regularization technique. I learned about this when trying to understand neural networks. I don't know if you have as well. It's just something they do between layers to make sure that stuff doesn't overfit. This is kind of like a form of that. They're harder to make because you have to add an extra cost function to get the data to cohere smoothly. Most very wait, brother, can you hear me?
yes, I can hear you. Yeah.
Okay, cool. All right, just making sure. Um, most variational autoencoders use something called the Kublik-Leibler divergence. It tries to get all the distributions to sort of be one distribution. However, it's a very simple function. There's actually some problems with it. Um, so Yeah, this explains more what's going on. So this is for traditional autoencoders. What happens is they have a set distribution. This is the white thing in the back. Can you see my mouse?
Yes, I can see your map.
Okay, good. And it tries to get the distribution of, so you have discrete data points, and they're mapped through distribution in latent space. And it tries to get each of those distributions to be kind of close to the standard one. Um, that's what um, that's what the KL divergence does. with the Wasserstein distance is instead of mapping each data point to a distribution, it maps each data point to a discrete point in the latent space, but tries to get the distribution of such data points in the latent space to be similar to the set distribution. And so this actually doesn't involve using the reparameterization trick that I think you showed me sometime earlier, where the whole creating a distribution from a point causes problems because you have a lot of random variables involved, and it makes gradient descent difficult. The Wasserstein distance doesn't have that problem because it pretty much tries to create a distribution of discrete data points that's similar to whatever standard distribution you give latency. And so this thing right here is the KL divergence. It's a very simple equation. Below here is the Wasserstein distance. It looks simple, but it's actually extremely complicated in practice. This is the infinitum, and then I don't know what the E stands for. It looks simple, but it's much more complicated than it looks. Yeah. There's also some certain properties of the Wasserstein distance that are better than the KL divergence because it's symmetrical. But that's why they use the term divergence for the KL instead of distance for the Wasserstein, because it's not really a distance. It's not. It's just kind of it measures the difference between two distributions. Wasserstein distance has a lot of mathematical properties that make it very helpful for modeling latent space. So I think you've actually shown me the slide too before.
Yeah.
The Wasserstein distance is pretty much just the best way to move from one distribution to another. And so what you'll have is you'll have a transportation plan where you have one distribution here, and you can map in this matrix however you want, as long as everything here adds up to this distribution, and everything across this way adds up to this distribution. So there's many different ways to do this. If you multiply this array times I'll show the next slide. If you multiply this array, which is the optimal transportation plan, this is the equivalent for a smooth distribution, not a discrete one, like I showed earlier. And you pretty much multiply each element here by each element in the cost matrix, which is pretty much the objective distance between two distributions. It will tell you pretty much the Wasserstein distance. And so you try to find an optimal transportation plan that, when multiplied by the cost matrix, gives you the lowest value possible, and that's the Wasserstein distance. So what else? Oh, and so this matrix here, since we're dealing with 1D distributions, it's 2D. What it basically is it's the dimensions of one distribution times, I think, added to the dimensions of the other. And so whatever form of autoencoder you have, your loss function is going to have take into account both error and distance or divergence. And so usually the equation takes is you have error times a certain constant. This is a hyperparameter. It's not trained. It's something that you would tweak individually according to how you want the latent space to be distributed. And then this would be the distance or divergence. But since we're working with Wasserstein, I'm using distance. And so, hold on. Okay, so then what I was thinking is I would train, since we're working with entropy alloys, I would train the autoencoder to have a latent space about 1 or 2 dimensions smaller than the sample space. This is so it would effectively model how the data is distributed without like overfitting. But what I would do instead is what I would try to do is make sure the data points with desirable traits cluster in the middle. And this is so once I'm done training, I could then sample from the center to the distribution as when I repurpose the decoder and the latent space as a generator. Actually, I think I have on this. Hold on, let's go here. So I would train it on composition, then I'd modify the latent space, and then I would use it as a generator and sample from the center of the latent space and try. And ideally, I would get a set of distributions that have more of the certain trait in question than I would on average. So this would help experimenters when they're sampling data, when they're choosing distributions to test experimentally. It would help them narrow the search. So let me go back. So what I would do to do this would be I would make sure when I'm calculating the Wasserstein distance, it would be tricked into believing that the data points that correspond to the compositions with good traits are further away than they actually are. And so this would make it want to bring them closer. So it would actually it would inadvertently make them cluster near the center because it would believe that they're further away from the center than they actually are. Probably different ways to go about this, but I think this would be the simplest way to do it. And so I would not be using, like Professor Cow told me a few days ago, I would not be using the paper that we were given to learn about the Wasserstein autoencoder from, because it pretty much has a 5-dimensional space with only 700 data points. So I don't know that a meaningful model could be created for that, although I'll probably test the concept. I'm actually testing different forms of it now on the paper, but I would not use it when I'm testing if it would work or not on such a sparse data set. So that's it. You have any questions or any slides you want me to go back to?
Yeah. Like what's your purpose? Do you have a purpose like for this? Or
Well, I was inspired by the paper because what they did was they went to they found spots in the latent space where the alloys had a low TEC,
mm-hmm,
or thermal coefficient of expansion. They
mm-hmm.
sampled 1,000 from those. Then they would run them through another neural network to narrow the search, and then they would test 3 of them.
Yeah.
So I'm kind of taking that principle and trying to generalize it, where it wouldn't be me searching through a two, because the thing is they have to make the latent space 2-dimensional so they can search for distributions. But in theory, I could have maybe a 10-dimensional space that would be transferred to an 8-dimensional latent space. And so searching for spots or islands where it has traits that I want wouldn't be very easy. But if I could trick it so that all of those islands that have good properties are clustered in the center, my model hopefully would also predict other compositions I haven't tested and
Right.
would predict that those would also be in the center. And so when I generate compositions, it would give me it would disproportionately give me good candidate compositions that people could test. I don't
Wait,
know if it would be used, but it's just an idea I'm
I
trying to.
I see. And what
I
dimension are you
except
going to? So like
what
what's the dimension for the latent space?
it would be 1 to 2 dimensions smaller than my
Then
sample space,
okay.
because
But
like
then
with a polynomial,
it's
you
not
you want
very
like
comprehensible.
it's not really what.
It's not very comprehensible. Like you can't really understand it. Right.
What do you mean the latent space?
Yeah, like if it's like a dimension, there's no way for you to understand it.
I agree. That's why I would try to cluster everything in the middle, and I would sample from the middle. I wouldn't know anything about the latent space.
Yeah, I mean even in the
This is what
middle. Like what does it mean to be in
what?
the middle of a dimension?
Oh, okay. So let me explain how this works.
Okay,
So
yeah, sorry.
no, it's fine. I shouldn't have overlooked this. So with the variational autoencoder, what it does is it gets the data to cluster around a set distribution that you specify for it. This is what
Mhm,
P of Z is, and then Q of Z is the distribution of all the data points. You see with my
mhm.
mouse?
Okay,
And so if I could trick the Wasserstein distance into believing that the distributions of data points with good traits are further away than they actually are, it will want to bring them closer. And so it will inadvertently place them all in the middle. And then all the compositions that have not so good traits would kind of be further out. And so once I'm done training, I would repurpose this as a generator and only sample from this spot in the latent space. And that
okay,
hopefully would give me better compositions than doing it on random.
okay. But like,
And so I wouldn't need to visualize the latent space to do this. And so my latent
okay.
space could be just slightly more compressed than it is in real life. And the reason I'd be slightly more compressed is to have the as detailed of a of a function as I can without overfitting. Like with polynomials and your modeling data, usually you actually want to have a polynomial that's like n minus 1 degrees. Because if it's n
And
degrees, it will fit every point and it won't tell you anything meaningful.
mm-hmm.
So that's kind of the line of thinking I'm going with. I actually emailed Professor
Okay.
Cow about this and he approved.
Oh, okay. I see.
Yeah.
I just still don't get the idea of like in the middle of high dimension, but like how just let's say just like num just on numbers, what does it what does it mean by like in the middle with high dimension? Like you have high dimension, so you have like 8 numbers in a vector, right? How does it
Well,
work
yeah,
like computationally?
it would be the vectors that have when most of their elements have values near zero. Like
Ah,
in
I
two
see.
dimensions, it's a circle.
Uh-huh.
In 3 dimensions, it's a sphere. In 4 dimensions, it's a hypersphere. And in 5 dimensions, it's a hypersphere. You know what I
Okay,
mean?
so
It's a
zero
lot of
is
these
near
distributions.
zero.
Yeah, you can move them to higher dimensions. So yeah.
Oh, okay, I see it. Okay, that makes sense. Okay, I see.
Yeah, so I
Higher
wouldn't have to
dimension.
visualize it. It would do all the work for me.
I see.
Um,
Okay, okay.
yeah.
That's
I
pretty
don't know
nice.
if it's worked. I don't know if
Yeah,
anyone's done this before, but it would be
yeah.
something to test.
Okay.
What I would do,
Let's
oh,
see.
go ahead.
Oh yeah, sorry. How do you plan to like evaluate? How do you test the accuracy? Or like
That's a good
what?
question. So what I would do is I would sample from, I'm trying to think how. Okay, so what I would do is I would generate a bunch of compositions.
Mm-hmm.
Um,
Would you generate or
well,
out
I'm
of
trying to think because they might not actually be data sets that are available. Um, what I do is I would map. Um, that's a good question. I had an idea, but I haven't thought this out enough. Um, well, the goal would maybe be to generate a bunch of compositions, and some of those would have already been tested. And so I would generate without doing that trick to cluster everything in the middle, and I would do it with doing that. And I would see if I would preemptively predict more compositions that actually are borne out in the data that I wouldn't train it on. So maybe I train on just a portion of a data set. And then I try to see if my model predicts things that are borne out in the rest of the data set, more so than not modifying it, or more so than random.
okay. But
So I could
well,
test it.
okay. But then like the amount of possible data is too much. So
What do
it's
you mean?
like well, I mean, how many dimensions are you working with? Yeah.
One or two less than the data set. So
Okay,
I
not too
actually
bad.
haven't looked at data sets yet. Maybe
Yeah.
if there's a composition of maybe like of entropy alloys with I don't know 10 different elements, my light space would be eight
Hmm.
or nine dimensions.
Yeah. Like, because for high dimension, the possible composition is too high compared to the one that we know. So even if you generate one, it's still pretty tricky to like confirm or like test it with the other composition that you currently have. Yeah.
Yeah, yeah. I mean, I'll
Yeah.
figure it out maybe later.
Yeah. I mean,
Um,
yeah. Anyways, yeah.
I haven't given too much thought about how I would actually test it though. I probably should have.
Yeah. I
Uh,
mean, yeah.
uh,
I mean, it's just like you will run into problems when you run the actual model and like, yeah, we'll see
yeah,
how things work out. Yeah.
yeah. I don't
Anyways,
want to have
yeah.
nothing to show for myself when by the end of the summer. But I think this is something that's kind of going off the paper did, but is quite different.
Yeah, it looks pretty good. Yeah. So for the Washington difference, Washington distance and the KL diversion, the main difference is just the probability distribution in the Leyland space, right?
Yeah, and the Wasserstein distance is more mathematically elegant. Like you don't do you know the parameterization trick you showed me?
Uh-huh. You don't need to do that.
You don't need to do that in the Wasserstein distance because
Mm-hmm.
all the spots in the data supposed to map to points. They don't map to
Mm-hmm.
distribution. It's
Okay.
about the distribution of discrete data points. And you try to get that distribution to be similar to the one you specified beforehand.
Okay. Yeah, there's a lot. So it's okay. I see.
Yeah.
Okay.
So the distribution of data points is Q, and the standard distribution you set beforehand is P.
Okay.
Um, and then with the VAE, there's a set of different P distributions,
Mm,
and you're basically the KL divergence is the sum of those. But with
okay.
Wasserstein distance,
That's
every data point treated as a whole distribution. So yeah.
I see. Yeah, it's more normal distribution. Okay. Uh, let me see. Any other question we can have? For what's the main like benefit of using WAE?
What?
Like, what's the main benefit? Because this is just like computational stuff, right? Just in more
Well,
general, what's the benefit?
so for entropy alloys, to test them experimentally, it's difficult because you have such a large space. And
Hmm.
so what I'm trying to do is my data set is the compositions of entropy alloys, and I would be changing the latent space based on a certain characteristic of from measured experiments we have. And
Hmm.
my goal is to try to generate a narrow composition that would help people narrow their search down because it would basically give them a set of candidates to experiment with. That
Mm,
would be better
I
than just
see.
going by random.
That's that's basically the paper. Right.
Not exactly, because well, because they're being specifically with TEC. My goal is to have
Hmm.
something very simple that could be generalized to a bunch of different applications. So
Ah,
I would
okay.
create my own program where it would take in like a vector of different properties from different compositions,
Hmm.
and it would find a way to trick the Wasserstein distance into clustering them in the center. I have a few ideas about that actually.
I see.
I might make a slide for it.
Okay. Yeah,
But yeah,
that could be nice. Yeah. Okay. Understood. Yeah. No. Yeah, it's just basically, oh wait, hold on. Let me think about it. Wait, what is the what is the autoencoder? No, what is the autoencoder does not use probability distribution. Hold on. You remember that?
or
Take
they can
it.
have something else.
Wait, no, I remember I present the what is the WAE before in the group meeting, but I don't remember the probability distribution. I think it's the paper. The paper didn't use, yeah, the paper didn't use probability, right? Yeah, the paper didn't use the
Did
probability.
wait? You talk about the reparameterization trick.
No, no, it's just the WAE. I don't remember any probability distribution. While the variation onto encoder, it does use a probability distribution, right?
Yeah, because okay, so because essentially what you're doing is you're finding the work it would take to move each data point to the middle of the distribution.
I see, right? So it's not
Whereas
a
whereas
probability,
well, it's a bit
right?
different.
Yeah, it's very different, right?
Whereas the KL divergent for this is kind of seeing where they overlap and where they don't overlap. Another
Yeah.
actually reason why Wasserstein's different than the KL divergence, because if any part of these distributions do not overlap, it will explode to infinity.
Mhm.
Because what you'll have
Mm.
is with this equation right here, you'll have this equation will either be 0 or infinity right here, because you'll have something here but nothing here, or nothing here and something here.
Oh, okay.
And log of 0 is negative infinity. And so either way, it's going to go to
Mm.
infinity or negative infinity if you don't have any overlap.
Okay.
So yeah,
Mm.
the
Okay.
Wasserstein distance doesn't have that exploding gradient problem.
Yeah. There's like, yeah. Okay, I see.
Yeah.
Yeah, because just look at the picture and it looks like a probability distribution for both of them. But then I realized like only the variation will have that probability distribution. And the WAE is not probability distribution.
What do you mean by that? Did I get something wrong?
No, for the WAE, it's not a probability distribution, right? I don't remember so.
Well, I mean, it kind of is. I mean,
Because it just minimize the loss function using the Wasserstein distance, and that's it. Like, there's no probability in there.
well, one way to think about it is they're kind of like the spots or well, yeah, I guess so. I guess it depends on because the thing is you can interpret a distribution any way you want, really. Um, I don't know what I'm talking about actually. I forget I said that. Do you mean like it's deterministic instead of indeterministic like the VAE? 'Cause yeah,
Yeah, so yeah, for variational turn encoder, you actually turn the number into a distribution, a probability distribution. So you have a mean and a mu, and then the other one is the what is that? Like the height of the distribution and thing like that. And then you try to make it similar to the normal distribution as much as possible with the KL diversion. And for
yeah.
Washington distance, it's not a probability distribution. You simply first you minimize the difference between the input and the output, and second, you simply minimize like a mathematical computation, which is the Wasserstein distance, and that's it. Like it doesn't have any distribution in it.
Well, I'd actually say it does. The standard distribution, the one that you specify beforehand that's not related to the data, is a probability distribution, and you're finding out the Earth mover's distance from each point to that distribution. So you're finding the distance to move each data point in this distribution to P of Z. but you're
Mm.
not turning the data points into a distribution. It's deterministic in that way.
Mm.
Yeah.
Let's see. Okay. Okay, let's do that rapid yet. Um, let's say on just a neural networks. Uh, let's see. How does it work on a neural networks? Do you have like a sample of neural networks? Let me check.
Like, what do you mean?
Because I'm trying to understand how WAE works. Because I did it before. I'm not really sure how.
I should look at the paper again because it used one. But what I think with variational autoencoders, how it has both the mean and the standard deviation.
Mm-hmm.
I think the Wasserstein's very much like the simpler ones where they just had just one vector instead of two.
Just one vector. What do
Yeah.
you mean by one vector? Like,
Well, the data points in a variational autoencoder turn to the mean in the standard deviation.
mm-hmm.
With the Wasserstein, it's deterministic. It's just like a plain autoencoder, except that
Okay.
the Wasserstein distance will instead of will make the spots in the data behave properly without treating them as distributions.
Okay. So it's deterministic for WAE then.
Yeah,
Okay.
it's
Okay.
like
That makes sense. Okay.
it's like a deterministic autoencoder that is getting the best, doing the things that a variational autoencoder would do, but
Okay.
it's
Okay.
deterministic.
Okay. That makes sense. Okay. Okay. No, I was
Yeah,
concerning about. Okay. All right.
yeah. I
Okay.
probably made it seem like the Wassersteins are a form of a variational autoencoder, and when I first started making the slide, I thought that they were. So I
Um,
probably should also clarify that more before I present this.
okay. Yeah. Okay. Yeah. All right. Nice.
All right, cool.
Uh, yeah. It's about 8 already. Yep.
I
All right.
know we're almost done.
Yeah. See you next Thursday.
Yeah, that sounds good. Or whenever
Yeah.
the meeting is.
Yeah. Yeah. Whatever. Yeah. Okay. All right. See you.
Yeah, later.